The next topic is brittleness. Brittleness is the tendency of a material to fracture with little or no plastic deformation. It breaks suddenly without much warning. This is important because the brittle fracture is abrupt and catastrophic. Designers must ensure parts have enough toughness, not just strength, in the expected service temperature and loading rate. It can be improved the brittleness by low temperature because ductile to brittle transition in many steels. The next one is high strain rate or impact. The next one is notches or defects. Notches or defects are the stress concentrators. To reduce the risk, specify toughness requirement, that means impact testing, and avoid sharp corners. So we can add fillets, then control defects and use appropriate preheat or post well heat treatment and tempering to refine microstructure. These factors or reduce the risk. Example is cast iron. Cast iron is a strong in compression but brittle under impact. So it can crack suddenly if struck. The next topic is creep. Creep means time dependent, slow, permanent deformation that occurs when a metal is held under a constant load at high temperature. It keeps straining even though the stress does not change. Typically, about 30 to 40% of the metal's melting temperature in Kelvin. Long service at heat, hours to years, makes creep a governing failure mode. In higher melting point and strong precipitate strengthening and large grains or single crystal to suppress grain boundary sliding. Protective coatings, that means oxidation accelerates creep and keeping actual stress low. These are the factors to control the creep resistance. The example is turbine blades in jet engines operate for long periods at very high temperature. So, materials and cooling designs are selected specifically to resist creep. Let me saw the creep curve. This is strain and this is time. Here this is the creep curve and here primary means it rates lows as work hardening builds. This is the minimum creep rate. Minimum creep rate strain divided by time at service time and stress. At the service, what are the strain and time we will keep. Then here is the secondary, that means steady and state. Steady state near the constant minimum creep rate, that means key design number. This is the constant temperature. Here this is a constant temperature, time to rupture. Example, already we saw the examples, turbine blades and steam pipes, also a example. Stage 1 is primary and stage 2 is secondary, stage 3 is tertiary. So, primary stage, the curve rises quickly, then the rate slows because the material work harden, so creep rate drops. The secondary stage is the curve is almost straight. This is the minimum or nearly constant. creep rate. The slope here is the key for life protection. Engineers size parts so they can run a long time in this region. Then territory, stage 3. The curve bends upward. Creep accelerates because damage builds, voids, micro cracks, necking, grain boundary sliding. So the failure is close. The time to rupture means the dashed vertical line marks when the specimen finally breaks at the stress and temperature. So this is the time to rupture. So the higher temperature or stress makes the curve steeper and shortens time to rupture. For hot parts, we pick creep resistant alloys and design so service stays in steady state. Creep with low rate well before territory damage begins. So this is the creep curve. The next topic is fatigue strength. The ability of a material to withstand many repeated, that means cycle loads without failing. Even stresses below yield can cause failure if applied 1000 to million of times. So how it happens means crack starts at a stress riser like a notch or hole, surface scratches, weld toe. Then crack grows a little each cycle and final fracture when the remaining section can't carry the load. It can improve by smooth transitions and polish or short peen and remove defects, good weld geometry and avoid sharp corners and use corrosion protection. So these are the key factors to improve the fatigue strength. And the example is aircraft wing components see constant cycle loads from lift and turbulence. So they are designed and inspected specifically for fatigue. So fatigue strength is about surviving millions of small hits, control stress rises and surface condition to stop cracks from starting and growing. This is a fatigue strength.